This is Lecture 5G for Calculus 1. It is a proof of the Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus is in two parts. Part 1. If f is continuous on the closed interval ab, then the function g of x defined by g of x equals the integral from a to x of f of t dt, where x is between a and b, is continuous on ab and differentiable on the open interval ab, and that the derivative of g is equal to f of x. Okay, note here that I'm using t, not because necessarily that the function is, that f is a function of time. The t here, remember, is a dummy variable of integration. It really doesn't matter. I could have used ta or nu or anything else, but I could not use x because x is up here as a limit of integration. Okay, so that's part 1. Part 2, if f is continuous on the closed interval ab, then the definite integral from a to b of f of t dt is equal to f evaluated b minus f evaluated a, and f is any antiderivative or primitive of f. That is, it is a function such that the derivative of f is equal to lowercase f. Of course, there's a correlation between g and f. But it's just, I'm stating it like that because f is any antiderivative. And remember that the functions, the antiderivative is really a family of functions. This proof for part 1 will rely on the squeeze or sandwich theorem. And note what needs to be proved. What needs to be proved is that g is a primitive of f, not this statement. This statement is a definition. Okay, we start with this definition, that g of x equals the integral from a to x of f of t dt. Then we remember the property of integrals, that you could break up an integral. So you're going from a to c, you could break that up into a to b, and then from b to c, and out of those two integrals. However, I'm going to use it in a subtraction sense. Okay, but I'll use that principle. Okay, what is g of x plus h? That, by this definition, that means I replace the x with x plus h. And g of x, we know above, looks like that. And if I subtract the two, what am I going to get? I'm going from a to x plus h, and then from a to x, and I'm subtracting, and I'm taking h to be greater than 0. Okay, so what I will get, it's as though I went all the way from 0 to, or from a to x plus h, and then I went part of the way there by going from 0 to x. What I end up with is the little part from x to x plus h. All right. Okay, I'm going to say h is strictly greater than 0, so I can divide by it. So I divide by it, and I have g of x plus h minus g of h over h equals 1 over h, times this integral, which is written wrong. Let me fix this. All right, that's fixed. So what we have here, after dividing by h, is that we have g at x plus h minus g at x divided by h. And that equals 1 over h times this little leftover integral here that we did through that subtraction and using the definition. I didn't fix that so good. There's actually only one t. It's not dtt, it's just dt. Okay. Now there was a property of an integral that if you had the global maximum and the global minimum, you could make a bound for that integral. You could say the integral from a to b is greater than the global minimum times b minus a, and it's less than the global maximum times b minus a. So let us write this as f at u and f at v, because in order to be a global max or global min, the function had to achieve that value. So we'll say it achieved the minimum at u and the maximum at v. We don't care what u and v are right now, it's just where it's achieved. So now I'm going to write this, which is just from the property of an integral. Right. Again, I could divide by h, and when I divide by h, I get this term in the middle, which is familiar. Let's go back and look at what it is. This was the term we were looking for that was in the middle, and here is what it is. It's that difference quotient on G. So we're going to substitute, of course, for the difference quotient on G. This on 2 slides. So here's what we ended up with. F at u, which was its minimum value, is less than or equal to 1 over h times this integral, which is less than or equal to f at v, which is its maximum value. I replace the middle part here with that difference quotient on G. Okay. Now the next obvious thing to do is let G go to 0. As G goes to 0, this function doesn't change because it has no h in it. This function doesn't change because it has no h in it. Alright, in fact, as h goes to 0, so here we are, we've replaced that middle term with the difference quotient on G. Right, and now we're going to take the limit as h goes to 0. Remember, u and v were in the interval x to x plus h. As h goes to 0, they become f of x. There we go. All right. As h goes to 0, this difference quotient becomes the derivative dg by dx. So by the squeeze theorem, we have this set up here, so we can use the squeeze theorem. F of x is less than or equal to the derivative of g, which is less than or equal to g of x. Okay, by the squeeze theorem, dg by dx equals f of x. And that's the proof of part 1. Here's a proof of part 2. I'm using the same proof as in Stewart, but I find it easier to use a C with the F instead of the C with the G. If you compare the two, you'll see what I mean. Okay, from part 1 we have this definition. And from part 1 we know that g of x is a primitive of f of x. We're going to let f of x be any other primitive of f of x. So this is true. If this is true, then the derivative of g equals the derivative of capital F, which equals f of x. The functions f and g differ at most by an additive constant. So I'm going to put the constant over here with c. So if g of x equals f of x plus c, the derivatives would be the same. And that's how we got the statement right here. Okay, at this point, we're going to use another property of the integral, that if you integrate over from a to a, the answer is 0. So g of a, because, let me erase this. This, by our definition, g was equal to the upper limit. Okay, and now we're saying that's 0 because we know the value of the integral here is 0. So I can use it to find the c in f. Right? So if g of a is 0 and f of a plus c is 0, c equals minus a. So then I could write, in general, g of x equals f of x minus f of a. If the upper limit is b, then I would have g of b equals this integral. But I know what g of b is, so here I have it. This is the second statement, second part of the fundamental theorem of calculus. A primitive evaluated at b minus a primitive evaluated at a equals the definite integral from a to b of f of t dt. Now I'll bet you didn't think those proofs would be so short. And the proofs are very short, but it was a concept that took people a long time to sort of wrap their minds around so they could write down the theorems.